What's up, everyone, and welcome. In this episode, we're going to talk about cognizant security systems. It's alive!
Oh, drat these computers. They're so naughty and so complex. I could pinch them.
It sounds like a scene from a spy thriller. An attacker gets through the IT defenses of a nuclear power plant and feeds it fake, realistic data, tricking its computer systems and personnel into thinking operations are normal. The attacker then disrupts the function of the key plant machinery, causing it to misperform or break down. By the time the system operators realize they've been duped, it's too late, with catastrophic results. The scenario isn't fictional. It happened in 2010 when the Stuxnet virus was used to damage nuclear centrifuges in Iran. And as ransomware and other cyber attacks around the world increase, system operators worry more about these sophisticated false data injection strikes. In the wrong hands, the computer models and data analytics based on artificial intelligence that ensure smooth operation of today's electric grids, manufacturing facilities, and power plants could be turned against themselves.
Rabbit season! Duck season! Rabbit season! Rabbit season! Duck season! Fire!
Purdue University's Hani Abdelkhalik has come up with a powerful response to make the computer models that run these cyber-physical systems both self-aware and self-healing. Using the background noise within these systems' data streams, Abdelkhalik and his students embed invisible, ever-changing, one-time use signals that turn passive components into active watchers. Even if an attacker is armed with a perfect duplicate of a system's model, any attempt to introduce falsified data will be immediately detected and rejected by the system itself, requiring no human response. We call it covert cognizance, said Abdelkhalik, an associate professor of nuclear engineering and researcher with Purdue's Center for Education and Research in Information Assurance and Security, CERIAS. Imagine having a bunch of bees hovering around you. Once you move a little bit, the whole network of bees responds, so it has that butterfly effect. Here, if somebody sticks their finger in the data, the whole system will know that there is an intrusion, and it will be able to correct the modified data. Abdelkhalik will be the first to say that he's a nuclear engineer, not a computer scientist. But today, critical infrastructure systems in energy, water, and manufacturing all use advanced computational techniques, including machine learning, predictive analytics, and artificial intelligence. Employees use these models to monitor readings from their machinery and verify that they are within normal ranges. From studying the efficiency of reactor systems and how they respond to equipment failures and other disruptions, Abdelkhalik grew familiar with the digital twins employed by these facilities, which are duplicate simulations of data monitoring models that help system operators determine when true errors arise. But gradually, he became interested in intentional rather than accidental failures, particularly what could happen when a malicious attacker has a digital twin of their own to work with. It's not a far-fetched situation, as the simulators used to control nuclear reactors and other critical infrastructure can be easily acquired. There's also the perennial risk that someone inside the system with access to the control model and his digital twin could attempt a sneak attack. So that is an attack from inside. Traditionally, your defense is as good as your knowledge of the model. If they know your model pretty well, then your defense can be breached, said Yenny Lee, a recent graduate from the group whose PhD research focused on the detection of such attacks using model-based methods. Abdelkhalik said, any type of system right now that is based on the control looking at information and making a decision is vulnerable to these types of attacks. If you have access to the data and then you change the information, then whoever's making the decision is going to be basing their decision on fake data.
Well, I guess I'm the goat.
To thwart this strategy, Abdelkhalik and Arvind Sundaram, a third-year graduate student in nuclear engineering, found a way to hide signals in the unobservable noise space of the system. Control models juggle thousands of different data variables, but only a fraction of them are actually used in the core calculations that affect the model's outputs and its predictions. By slightly altering these non-essential variables, their algorithm produces a signal so that individual components of a system can verify the authenticity of the data coming in and react accordingly. When you have components that are loosely coupled with each other, the system really isn't aware of the other components or even of itself, Sundaram said. It just responds to its inputs. When you're making it self-aware, you build an anomaly detection model within itself. If something is wrong, it needs to not just detect that, but also operate in a way that doesn't respect the malicious input that's come in, so it just throws it away. For added security, these signals are generated by the random noise of the system hardware, for example, fluctuations in temperature or power consumption. An attacker holding a digital twin of a facility's model could not anticipate or recreate these perpetually shifting data signatures. Your CPU goes up and down. The temperature of your CPU or of your machine changes regularly. They can't recreate that. And even someone with internal access would not be able to crack the code. Anytime you develop a security solution, you can trust it, but you still have to give somebody the keys, Abdelkhalik said. If that person turns on you, then all bets are off. Here, we're saying that the added perturbations are based on the noise of the system itself. So there's no way I would know what the noise of the system is, even as an insider. It's being recorded automatically and added to the signal. Though the papers published by the team members so far have focused on using their paradigm in nuclear reactors, the researchers see potential for applications across industries. Any system that uses a control loop and sensors, Sundaram said. The same methods could be used also for objectives beyond cybersecurity, such as self-healing anomaly detection that could prevent costly shutdowns, and a new form of cryptography that would enable the secure sharing of data from critical systems with outside researchers. Abdelkhalik and Sundaram have begun to explore the commercial possibilities of covert cognizance through a startup company. That startup, Covert Defenses LLC, has recently engaged with Entanglement Incorporated, an early-stage deep tech company, to develop a go-to-market strategy. Now, when I first read this article, my mind exploded with ideas. It has inspired me to look at our models in a different way. So, what did we learn? Well, most of our security models today are still purely reactive. Meaning something changes, we recognize it, and we react. There are few, if any, security products out there that integrate a type of cognizant layer into their structure. Right now, for example, systems would have a listener to say a Windows registry key to see if it is being manipulated for Internet Explorer or something like that. Then they'd block that change. Or they look for specific signatures on applications that are installed or downloaded onto the system based on known information. But what if all activity is mixed with signals specific to an individual machine, based on CPU speed, temperature, historical data, or usage, etc.? And then those signals would be able to prevent tampering, since nobody can know what the signal mesh is at any time except for the machine in question. Now, there are tons of applications where work like this can be implemented into enterprise systems right now. Now, not just power grids or nuclear plants or water treatment plants, but interactions or databases, web systems, you name it. Now, this is probably a few years off, but the idea of having a cognizant security defense system is an amazing thing to work towards. And hopefully I was able to stimulate your brains into thinking of how you could use something like this as well. With that, I say thanks for watching. Don't forget to share and subscribe if you haven't already, and smash the bell if you haven't already. And I'll see you on the next episode. Take care.